Hello everyone, thank you for listening my presentation. My name is Kai Liu from University of Florida. Today I will talking about my course project in network science and applications. My project name is called Graph Community Detection, a Scalable Approach and Application. My proposed project is to build a scalable MapReduce algorithm for the graph clustering and community detection problems. The requirement for our developed algorithm is that we want to build a new algorithm and suitable for the big data requirement, and we could make it applicable to real applications. Our approach is to develop a new MapReduce algorithm. We call it inference and conquer, and we apply this algorithm to some really large data set. There are lots of work talking about the community detections. However, for the online social networks with 1 million users, the adjacency matrix input is about terabytes. So, but all this existing community detection algorithm is only suitable for the single machine version. So how to scale it? Our approach is that we need a scalable algorithm with high time efficiency. We also need to use the MapReduce programming model, which is very suitable for data-intensive computing and make these algorithms runnable in the Hadoop clusters. Another problem is that for real applications like community detection in Twitters, we don't have any pairing information about the number of clusters or communities. But the existing clustering algorithms like the k-means, you need to input the number of key. That you need these pairing informations. So we need to build a new algorithm that with no pairing information requirement. The community detection has a lot of application. For example, you can perform community detection for Twitters to perform the friend recommendation or even marketing by finding the most influential persons. You also can classing the tweet streams according to topics or classing the searched tweets. For example, if you want to search what's happening right now, you type Obama. Then you have lots of tweets available for the Obamas. All these search results is based on the stream matching. But actually, we can perform the clustering or community detection to classify all these tweets into different categories. So you can browse all these tweets in a very efficient way. So the fundamental problem for this kind of application is you need to determine the clusters or determine the number of communities. We need an algorithm that is really fast enough and time efficient. And we also need this kind of algorithm that is suitable for large data sets and requires no pattern information. Another problem is that we actually can implement our algorithms and integrate it into the Mahout machine learning library, so we can make it more suitable for other applications. This is the MapReduce programming models. So how to determine the clusters? Label propagation was first proposed in physical review in 2007, and it is a very time-efficient algorithm that needs no pairing information of the community structures. It's only the network structure itself to guide the community detections. This algorithm doesn't optimize any global measure or any other functions. And the process of the label propagation is that each node finds a neighboring community to the largest set to join until the system reaches an equilibrium. There are already one MapReduce implementations of the label propagation. They also proposed a scalable version of using Hadoop cluster with 15 nodes and applied to real dataset for the Twitters containing 14 million users and 1.4 billion connections. Each node has 16 GHz memory to meet the high memory requirement. The problem for this MapReduce implementation is that they also completely follow the initial single machine algorithms of the label propagations. And And it also uses a global label tables to store and update all the labels for the users. Like this figure shows that for every mapper, you need to ship this global table of labels to every mapper. So for every single machine, you need to load these labels into its memory. So if for larger dataset, the table of the labels could be also very large. So this kind of algorithm is really has a high requirement on the memory and has achieved very low scalability. So we want to build a new algorithms and make it suitable for the MapReduce programming models. The basic idea is that we want to make it scalable and perform the put or inference process instead of the get process in the label populations. The reason that we need to perform put, we want to make it more suitable for the MapReduce algorithm. The rationale behind this inference and conquer algorithm is that it's just like a social racing. So in the first step, every user wants to influence others. The others means the users followers, and conquer these followers as their own community members. For every user, he may receive lots of influences. Then he want to update his own labels, and according to all the received influences, then he chooses a new label value. So after this kind of several iterations, the whole network will reach to equilibrium, and the labels remains in this network reveal these community structures. So we slightly revise the input adjacency list. We do not add the label value into the adjacency list to eliminate the requirement of the global label table. So for the map output, we output we have all the followers and his received inferences and its associated labels. To maintain this graph connection, so we also output the adjacency list into the mapper process. Then the mapper process determines a new labels for the followers and update it into this adjacency list. Then this new adjacency list is the input for the next iterations. So using such kind of process, we embedded the label values into the adjacency list. And using the Hadoop mechanisms like aggregate the key values, for example, the map process will automatically aggregate all the key values. By utilizing such kind of Hadoop internal mechanisms, we can eliminate the use of the global values and make it more scalable. We evaluate over algorithms in two different datasets. The first one is a very small scale dataset. It is the Kata Club network. The second dataset is about the Twitter user network with 40 million users and 1.4 billion connections. We can use the Kata dataset to illustrate the process of the label over inference and conquer process. In the first step, every user may have its own labels. Then after several iterations, every user's only 3 labels exist. So we can see that there are only 3 communities. This is the community structures. After test with this small scale dataset, we directly apply our algorithms into this Twitter user network with 40 million users and 1.4 billion connections. We will run our algorithms on Amazon EC2 with 6x large instances. The total running time is about 8 hours and 35 minutes. So it is very fast. Only takes about 8 hours to perform. We can obtain the community result for this kind of really large Twitter user network. This is obtained community size distributions. The x-axis shows as the members per community. The y-axis shows as the community numbers. So we can see from this figure, we can show that it is kind of the heavy tier distributions. If we're using the log values for the y, so we can obtain this kind of linear figures. And this figure can be divided into 3 regions. For the first regions, we see it is a small sized communities. For Twitter, there are lots of users. There are lots of inactive users. They only have very few followers. So the users in this kind of small size community is about 1 to 64 members. There are also 1 million sized communities. The users in this community is about 64 to 1024. The second region is the larger sized communities. The users in this community is larger than 1000. So by developing a new community detection algorithms, and we apply it to the large data set, we can obtain some insights about this community size distributions. We can know that the users in the Twitters also follow this kind of heavy tier distribution, and the community size distribution could be divided into 3 regions, that is small region, medium sized region, and large sized regions. That's in my presentation. Thank you.